Welcome to the video lecture for Unit 3, Module 7.6. In this one, we're going to talk about the control of respiration, respiratory system integration, and the effects of aging on the respiratory system. As always, you can see our learning objectives here. Please utilize these to help study for your lecture quiz as well as your unit exam. Let's go ahead and get started. Peripheral cells continuously absorb oxygen and generate carbon dioxide. Under normal conditions, the cellular rates of absorption and generation are matched by the capillary rates of delivery and removal. Both rates are identical to those of oxygen absorption and carbon dioxide excretion at the lungs. If the diffusion rates of peripheral and alveolar capillaries become unbalanced, homeostatic mechanisms intervene to restore equilibrium. Such mechanisms involve 1. Changes in blood flow and oxygen delivery that are regulated at the local level, and 2. Changes in the depth and rate of respiration under the control of the brain's respiratory centers. The activities of the respiratory centers are coordinated with changes in cardiovascular function, such as fluctuations in blood pressure and cardiac output. The rate of oxygen delivery in each tissue and the efficiency of oxygen pickup at the lungs are largely regulated at the local level. For example, when a peripheral tissue becomes more active, the interstitial PO2 falls and the PCO2 rises. This change increases the difference between the partial pressures in the tissues in the arriving blood. As a result, more oxygen is delivered and more carbon dioxide is carried away. In addition, the rising PCO2 levels cause the relaxation of smooth muscles in the walls of the arterioles and the capillaries in the area, increasing local blood flow. At the lungs, local factors coordinate 1. Lung perfusion, or blood flow to the alveoli, with 2. Alveolar ventilation, or airflow. This local coordination takes place over a wide range of conditions and activity levels. As blood flows towards the alveolar capillaries, it is directed towards lobules with a relatively high PO2. This movement takes place because alveolar capillaries constrict when the local PO2 is low. Also in the lungs, smooth muscles in the walls of the bronchioles are sensitive to the PCO2 of the air they contain. When the PCO2 goes up, the bronchioles increase in diameter, or bronchodilation. When the PCO2 declines, the bronchioles constrict, or bronchoconstriction. Airflow is therefore directed to lobules with a high PCO2. These lobules get their carbon dioxide from the blood and are actively engaged in gas exchange. The response of the bronchioles to PCO2 is especially important because improvements in airflow to functional alveoli can at least partially compensate for damage to pulmonary lobules. Local adjustments improve the efficiency of gas transport by directing blood flow to alveoli with low CO2 levels and increasing airflow to alveoli with high CO2 levels. These adjustments in alveolar blood flow and bronchial diameter take place automatically. When activity levels increase and the demand for oxygen rises, the cardiac output and the respiratory rates increase under neutral control. Respiratory control has both involuntary and voluntary components. Your brain's involuntary centers regulate the activities of the respiratory muscles. These centers control the respiratory minute volume by adjusting the frequency and depth of pulmonary ventilation. They make these adjustments in response to sensory information arriving from your lungs and other parts of the respiratory tract, as well as from a variety of other sites. The voluntary control of respiration reflects activity in the cerebral cortex. This activity affects the output of either the respiratory centers in the medulla oblongata and the pons, or motor neurons in the spinal cord that control respiratory muscles. The respiratory centers are 3 pairs of nuclei in the reticular formation of the medulla oblongata and the pons. The motor neurons in the spinal cord are generally controlled by respiratory reflexes, but they can also be controlled voluntarily through the commands delivered by the corticospinal pathway. Each respiratory rhythmicity center can be subdivided into a dorsal respiratory group, or a DRG, and the ventral respiratory group, or the VRG. The DRG is chiefly concerned with inspiration, whereas VRG is primarily associated with expiration. The DRG functions in every respiratory cycle, whether quiet or forced. The DRG's inspiratory center contains neurons that control lower motor neurons innervating the external intercostal muscles and the diaphragm. The VRG functions only during forced breathing. It has an expiratory center consisting of neurons that innervate lower motor neurons controlling accessory respiratory muscles involved in active exhalation. Its inspiratory center contains neurons involved in maximal inhalation, such as gasping. Reciprocal inhibition takes place between the neurons involved in inhalation and exhalation. When the inspiratory neurons are active, the expiratory neurons are inhibited, and vice versa. The pattern of interaction between these groups differs between quiet breathing and forced breathing. So during quiet breathing, activity in the DRG increases over a period of about 2 seconds, stimulating the inspiratory muscles. Over this period, inhalation takes place. After 2 seconds, the DRG neurons become inactive. They remain quiet for the next 3 seconds and allow the inspiratory muscles to relax. Over this period, passive exhalation takes place. During forced breathing, increases in the activity of the DRG stimulate neurons of the VRG that activate the accessory muscles involved in inhalation. After each inhalation, active exhalation takes place as the neurons at the expiratory center stimulate the appropriate accessory muscles. The basic pattern of respiration thus reflects a cyclic interaction between the DRG and the VRG. However, the timing of this interaction is highly variable, and current research suggests that respiratory rate and rhythm cannot be attributed to a single area. The nuclei involved in respiratory control form a complex network that includes 1. The rhythmicity centers, 2. The centers in the pons that are modulated by peripheral and higher center inputs, and 3. An area in the ventrolateral medulla known as the central pattern generator or the P-Botzinger complex that's essential to all forms of breathing. There are reciprocal pathways between these nuclei, and deciphering the communication is extremely difficult, and the patterns change with different situations. Central nervous system stimulants, such as amphetamines or even caffeine, increase the respiratory rate by facilitating the respiratory centers. These actions are opposed by CNS depressants, such as barbiturates or opiates. Respiratory control is an area of intense study, and our understanding of the interactions and mechanisms remains largely incomplete. Due to the brainstem locations, it's nearly impossible to study this mechanism in humans, and much of the work has been done in cats and newborn rodents. The apneustic centers and the pneumotaxic centers of the pons regulate the depth and rate of respiration in response to sensory stimuli or input from other centers of the brain. Each apneustic center provides continuous stimulation to the DRG on that side of the brainstem. During quiet breathing, the stimulation from the apneustic center helps increase the intensity of inhalation over the next 2 seconds. Under normal conditions, after 2 seconds, the apneustic center is inhibited by signals from the pneumotaxic center on that side. During forced breathing, the apneustic centers also respond to sensory input from the vagus nerves regarding the amount of lung inflation. The pneumotaxic centers inhibit the apneustic centers and promote passive or active exhalation. Centers in the hypothalamus and the cerebrum can alter the activity of the pneumotaxic centers, as well as the respiratory rate and depth. However, essentially normal respiratory cycles continue even if the brainstem superior to the pons has been severely damaged. In some cases, the inhibitory output of the pneumotaxic centers is cut off by a stroke or other damage to the brainstem, or sensory innervation from the lungs is eliminated due to damage in the vagus nerves. In these cases, the person inhales to maximum capacity and maintains that state for 10 to 20 seconds at a time. Innervating exhalations are brief, and little pulmonary ventilation occurs. Interactions between the DRG and the VRG establish the basic pace and depth of respiration. The pneumotaxic centers modify that pace. An increase in pneumotaxic output quickens the pace of respiration by shortening the duration of each inhalation. A decrease in pneumotaxic output slows the respiratory pace, but increases the depth of respiration because the apneustic centers are more active. Sudden infant death syndrome, or SIDS, also known as crib death, is the leading cause of death for babies from 1 to 12 months old, and it kills over an estimated 2,250 infants a year in the United States alone. Most crib deaths occur between midnight and 9 a.m. in the late fall or winter and involve infants 2 to 4 months old. Eyewitness accounts indicate that the sleeping infant suddenly just stops breathing, it turns blue or goes cyanotic, and then relaxes. Genetic factors appear to be involved, but controversy remains to the relative importance of other factors. The age at the time of death corresponds with a period when the pacemaker complex and the respiratory centers are establishing connections with other portions of the brain. It's been suggested that SIDS results from a problem in the interconnection process that disrupts the reflexive respiratory pattern. The activities of the respiratory centers are modified by sensory information from several sources. Chemoreceptors sensitive to the PCO2, pH, or PO2 of the blood in cerebrospinal fluid, baroreceptors in the aortic or the carotid sinuses sensitive to changes in blood pressure, stretch receptors that respond to changes in the volume of the lungs, irritating physical or chemical stimuli in the nasal cavity, larynx, or the bronchial tree, and other sensations including pain, changes in body temperature, and abnormal visceral sensation. Information from these receptors alters the pattern of respiration. The induced changes have been called respiratory reflexes. The respiratory centers are strongly influenced by chemoreceptor inputs from the cranial nerves 9 and 10, and from receptors that monitor the composition of the CSF. The glossopharyngeal nerves carry chemoreceptive information from the carotid bodies adjacent to the carotid sinus. The carotid bodies are stimulated by a decrease in the pH, or PO2 of the blood. Because changes in PCO2 affect pH, an increase in PCO2 indirectly stimulates these receptors. The vagus nerve monitor the chemoreceptors in the aortic bodies near the aortic arch. These receptors are sensitive to the same stimuli as the carotid bodies. Carotid and aortic body receptors are often called peripheral chemoreceptors. Chemoreceptors are located on the ventrolateral surface of the medulla oblongata in a region known as the chemosensitive area. The neurons in that area respond only to PCO2 and the pH of the CSF. They are often called central chemoreceptors. Stimulation of these chemoreceptors leads to an increase in the depth and rate of respiration. Under normal conditions, a drop in arterial PO2 has little effect on the respiratory centers until the arterial PO2 drops by about 40% to below 60. If the PO2 of arterial blood drops to 40, which is the level in peripheral tissues, the respiratory rate increases by only 50 to 70%. In contrast, a rise of just 10% in the arterial PCO2 causes the respiratory rate to double, even if the PO2 remains completely normal. Carbon dioxide levels are therefore responsible for regulating respiratory activity under normal conditions. Although the receptors monitoring CO2 levels are more sensitive, oxygen and carbon dioxide receptors work together in a crisis. Carbon dioxide is generated during oxygen consumption, so when oxygen concentrations are falling rapidly, CO2 levels are usually increasing. This cooperation breaks down only under unusual circumstances. For example, you can hold your breath longer than normal by taking deep, full breaths, but the practice is very dangerous. The danger lies in the fact that their increased ability is due not only to extra oxygen, but to less carbon dioxide. If the PCO2 is driven down far enough, your ability to hold your breath can increase to the point at which you become unconscious from oxygen starvation in the brain without ever feeling the urge to breathe. The chemoreceptors are subject to adaptation, a decrease in sensitivity after chronic stimulation, if the PO2 or the PCO2 remains abnormal for an extended period of time. This adaptation can complicate the treatment of chronic respiratory disorders. For example, if the PO2 remains low for an extended period while the PCO2 remains chronically elevated, the chemoreceptors will reset to those values. They will then oppose any attempts to return the partial pressures to the proper range. Any condition altering the pH of blood or the CSF affects respiratory performance because the chemoreceptors monitoring CO2 levels are also sensitive to pH. The increase in lactic acid levels after exercise, for example, cause a decrease in pH that helps stimulate respiratory activity. Hypercapnia is an increase in the PCO2 of arterial blood. Stimulation of chemoreceptors in the carotid and aortic bodies triggers this response. It is reinforced by the stimulation of the CNS chemoreceptors. Carbon dioxide crosses the blood-brain barrier quite rapidly. For this reason, a rise in arterial PCO2 almost immediately increases CO2 levels in the CSF, decreasing the pH of the CSF and stimulating the chemoreceptive neurons of the medulla oblongata. These chemoreceptors stimulate the respiratory centers to increase the rate and depth of respiration. Your breathing becomes more rapid, and more air moves into and out of your lungs with each breath. Because more air moves into and out of the alveoli each minute, alveolar concentrations of carbon dioxide decline, accelerating the diffusion of carbon dioxide out of the alveolar capillaries. In this way, homeostasis is restored. The most common cause of hypercapnia is hypoventilation. In hypoventilation, the respiratory rate remains abnormally low and cannot meet the demands for normal oxygen delivery and carbon dioxide removal. Carbon dioxide then accumulates in the blood. If the rate and depth of respiration exceeds the demands for oxygen delivery and the carbon dioxide removal, the condition called hyperventilation exists. Hyperventilation gradually leads to hypocapnia and abnormally low PCO2. If the arterial PCO2 drops below normal levels, chemoreceptor activity decreases and the respiratory rate falls. This situation continues until the PCO2 returns to normal and homeostasis is restored. So we described the effects of the carotid and aortic baroreceptor stimulation on systemic blood pressures in Module 5. The output from these baroreceptors also affects the respiratory centers. When blood pressures fall, the respiratory rate increases. When blood pressures rise, the respiratory rate decreases. These adjustments result from the stimulation or inhibition of the respiratory centers by sensory fibers in the glossopharyngeal and the vagus nerves. The Hering-Bauer reflexes are named after the physiologist who described them in 1865. The sensory information from these reflexes goes to the apneustic centers and the ventral respiratory group. The Herring-Brewer reflexes are not involved in normal quiet breathing, or eupnea, or in tidal volumes under 1,000 milliliters. There are two such reflexes. One, the inflation reflex prevents overexpansion of the lungs during forced breathing. Lung expansion stimulates stretch receptors in the smooth muscle tissue around the bronchioles. Sensory fibers from the stretch receptors of each lung reach for the respiratory rhythmicity centers on the same side by the vagus nerve. As lung volume increases, the dorsal respiratory group is gradually inhibited, and the expiratory center of the VRG is stimulated. Inhalation stops as the lungs near maximum volume. Active exhalation then begins. And two, the deflation reflex normally functions only during forced exhalation, when both the inspiratory and the expiratory centers are active. This reflex inhibits the expiratory centers and stimulates the inspiratory centers when the lungs are deflating. These receptors are distinct from those in the inflation reflex. They are located in the alveolar wall near the alveolar capillary network. The smaller the volume of the lungs, the greater the degree of inhibition. Finally, exhalation stops and inhalation begins. Protective reflexes operate when you're exposed to toxic vapors, chemical irritants, or mechanical stimulation of the respiratory tract. The receptors involved are located in the epithelium of the respiratory tract. Examples of protective reflexes include sneezing, coughing, and laryngeal spasms. Sneezing is triggered by an irritation of the nasal cavity wall. Coughing is triggered by an irritation of the larynx, trachea, or bronchi. And both reflexes involve apnea, which is a period which respiration is suspended. A forceful expulsion of air usually follows to remove the offending stimulus. The glottis is forcefully closed while the lungs are still relatively full. The abdominal and internal intercostal muscles then contract suddenly, creating pressure that blasts air out of the respiratory passageways when the glottis reopens. Air leaving the larynx can travel at 160 kilometers per hour, carrying mucus, foreign particles, and irritating gases out of the respiratory tract via the nose or the mouth. Laryngeal spasms result when the chemical irritants, foreign objects, or fluids enter an area around the glottis. This reflex generally closes the airway temporarily. A very strong stimulus, such as a toxic gas, could close the glottis so powerfully that you could lose consciousness and die without taking another breath. Fine chicken bones or fish bones that pierce the laryngeal walls can also stimulate the laryngeal spasms, swelling, or both, which also restricts the airway. Activity of the cerebral cortex has an indirect effect on the respiratory centers, as the following examples show. Conscious thought processes tied to strong emotions, such as rage or fear, affect the respiratory rate by stimulating centers in the hypothalamus. Emotional states can affect respiration by affecting the sympathetic or the parasympathetic division of the autonomic nervous system. Sympathetic activation causes bronchodilation and increases the respiratory rate, while parasympathetic stimulation has the opposite effect. An anticipation of strenuous exercise can trigger an autonomic increase in the respiratory rate, along with increased cardiac output by sympathetic stimulation. Conscious control over respiratory activities may bypass the respiratory centers completely, using the pyramidal fibers that innervate the same lower motor neurons that are controlled by the DRG and the VRG. This control mechanism is an essential part of speaking, singing, and swimming, when respiratory activities must be precisely timed. Higher centers can also have an inhibitory effect on the apneustic centers and on the DRG and the VRG. This effect is important when you hold your breath. Your abilities to override the respiratory centers have limits, however. The chemoreceptor reflexes are extremely powerful in stimulating respiration, and you cannot consciously suppress them. For example, you cannot kill yourself by holding your breath until you turn blue. Once the PCO2 increases to critical levels, you're forced to take a breath. The respiratory systems of fetuses and newborns differ in several important ways. Before delivery, pulmonary arterial resistance is high because the pulmonary vessels are collapsed. The rib cage is compressed and the lungs and conducting passageways contain only small amounts of fluid and no air. During delivery, the lungs are compressed even further. As the placental connection is lost, blood oxygen levels fall and carbon dioxide levels climb rapidly. At birth, the newborn infant takes a truly heroic first breath through powerful contractions of the diaphragmatic and the external intercostal muscles. The inhaled air must enter the respiratory passageways with enough force to overcome surface tension and inflate the bronchial tree and most of the alveoli. The same drop in pressure that pulls air into the lungs also pulls blood into the pulmonary circulation. The changes in blood flow and rise in oxygen levels lead to the closure of the foramen ovale and the interatrial connection, and the ductus arteriosus, the fetal connection between the pulmonary trunk and the aorta. The exhalation that follows does not empty the lungs completely because the ribcage does not return to its former fully compressed state. Cartilages and connective tissues keep the conducting passageways open, and surfactant covering the alveolar surfaces prevents their collapse. The next breaths complete the inflation of the alveoli. Pathologists sometimes use these physical changes to determine whether a newborn infant died before delivery or shortly thereafter. Before the first breath, the lungs are completely filled with amniotic fluid, and the extracted lungs will sink if placed in water. After the infant's first breath, even if the collapsed lungs contain enough air to keep them afloat. Many factors interact to reduce the efficiency of the respiratory system in elderly individuals. Here are 3 examples. 1. With age, elastic tissue deteriorates throughout the body. These changes reduce the compliance of the lungs and lower vital capacity. 2. Chest movements are restricted by arthritic changes in the rib articulations and by decreased flexibility at the costal cartilages. Along with the elastic tissue deterioration, the stiffening and reduction in chest movement effectively limit the respiratory minute volume. This constriction contributes to the reduction in exercise performance and capabilities with increasing age. And 3. Some degree of emphysema is normal in individuals over age 50. However, the extent varies widely with the lifetime exposure to cigarette smoke and other respiratory irritants. This graph compares the respiratory performance of individuals who have never smoked with individuals who have smoked for various periods of time. The message is quite clear. Some decrease in respiratory performance is inevitable, but you can prevent serious respiratory deterioration by stopping smoking or never starting to begin with. The goal of respiratory activity is to maintain homeostatic oxygen and carbon dioxide levels in peripheral tissues. Changes in respiratory activity alone are seldom enough to accomplish this. Coordinated changes in cardiovascular activity must take place. Consider these examples of the integration between respiratory and cardiovascular systems. At the local level, changes in lung perfusion in response to changes in alveolar PO2 improve the efficiency of gas exchange within or among lobules. Chemoreceptor stimulation not only increases the respiratory drive, but it also causes blood pressure to rise and cardiac output to increase. The stimulation of baroreceptors in the lungs has secondary effects on the cardiovascular function. For example, the stimulation of airways stretch receptors not only triggers the inflation reflex, but also increases heart rate. Thus, as the lungs fill, cardiac output rises and more blood flows to the alveolar capillaries. The adaptations that take place at high altitudes are an excellent example of the functional interplay between the respiratory and cardiovascular symptoms. Atmospheric pressure decreases with increasing altitude, and so do the partial pressures of the component gases, including oxygen. People living in Denver or Mexico City function normally with alveolar oxygen pressures in the 80 to 90 range. At higher elevations, alveolar PO2 is even lower. At 3,300 meters, an altitude many hikers and skiers have experienced, alveolar PO2 is about 60. Despite the low alveolar PO2, millions of people live and work in altitudes this high or higher. Important physiological adjustments include increasing respiratory rate, increasing heart rate, increasing BPG levels, and elevated hematocrit. Thus, even though the hemoglobin is not fully saturated, the bloodstream holds more of it, and the round trip between the lungs and the peripheral tissues takes less time. However, most of these adaptations take days to weeks to develop. As a result, athletes planning to compete in events in high altitudes must begin training under such conditions well in advance.